14,000 miles of wire. That is what has held the Brooklyn Bridge against the sky for more than a century. What appears to be magic is pure, uncompromising engineering. A single one of its main cables, barely thicker than a human arm, carries the weight of thousands of cars. It endures the constant assault of hurricane-force winds, a force that makes the entire structure vibrate with a deep, resonant hum, a relentless load, day after day. It is a paradox of scale and strength, a steel thread defying gravity and time. This is not magic. This is a formula, written in steel. But how is that formula created? How do you transform simple rock into the unbreakable sinew of civilization? The secret lies not in its size, it's in its blood. To create this invulnerable cable, we must start at the heart of the megafactory. We descend into the electric arc furnaces, where at 1,600 degrees Celsius, the bridge's chemical armor is born. The heart of this operation is a fortress of steel, an electric arc furnace rising to the height of a 5-story building. Inside, thousands of tons of purified ore and high-grade scrap metal await a violent transformation. Giant graphite electrodes plunge into the metal. A massive electric current leaps between them, a blinding flash. The furnace ignites, unleashing an arc hotter than the surface of the sun. Solid steel melts into a viscous, brilliant mass, flowing with the thick energy of volcanic lava. But this is not just melting, it is alchemy. Here, in this controlled inferno, chemical science dictates the cable's destiny. Engineers add a precise cocktail of alloys to engineer its final properties. Manganese is added to increase hardness and fight abrasion. Chromium and nickel form a shield, an invisible armor against corrosion and rust. And silicon is introduced to improve ductility, the steel's ability to stretch under extreme load without fracturing. A protective layer of slag floats on the surface, a natural filter absorbing impurities from the boiling steel. Once refined, the liquid steel is drained. It's channeled through water-cooled copper molds, solidifying from the outside in. The result is a square steel billet, pure alloy. Red hot and glowing, they crash from their forms, ready for the immense pressures that come next. But to feed this 5-story furnace, industry must commit violence against nature, tearing millions of tons of raw rock from the Earth's crust. The process begins not in a factory, but with a millimeter-perfect calculation. High-power drills pierce solid rock, creating cavities for industrial explosives. Then, a controlled detonation. The mountain is ripped apart. A deafening roar echoes as the Earth fractures, releasing enormous blocks of iron ore, identifiable by a characteristic reddish hue, the signature of oxidized metal. Mining titans move in. Hydraulic excavators with shovels the size of a small room scoop the shattered rock, loading haul trucks that carry hundreds of tons of payload. In a single trip, these giants travel dedicated routes to colossal hoppers, where the raw material is subjected to rigorous mechanical refinement. The relentless grinding of crushers fills the air. Here, a flash of magnetic force separates metal from waste. Powerful magnetic separators extract the valuable iron from the gangue, discarding impurities like sand and clay. The concentrated ore is then shipped, a constant flow of raw material feeding the steel mills. This supply is relentless. The industry cannot afford to stop its furnaces for a single second, continuing to devour entire mountains. When rock torn from the earth is purified and solidifies after 1,600 degrees Celsius into perfect blocks, it faces the mechanical meat grinder of the rolling mill. The freshly forged billets still glow an incandescent orange, radiating a scorching heat as they are fed into a synchronized line of massive alloy rollers. This is hot rolling, a process of brutal, controlled violence. With each pass, the rollers apply thousands of tons of pressure, a force equivalent to a stack of locomotives on a surface the size of a dinner plate. This immense compression is a form of microforging. It violently realigns the steel's internal grain structure, collapsing microscopic pores and voids left over from the casting process. The metal gives way, density increases. Strength is born from this pressure. What began as a clumsy square block is instantaneously stretched and squeezed, shooting out the other side as a single continuous, perfectly round profile. A new geometry. This is the wire rod, the raw material for the cable itself. But the transformation is delicate. If the steel cools too fast, it could crack, creating invisible weaknesses that would doom the entire project. The pressure of thousands of tons has set its new form, but the steel is now trapped on the edge of its physical limit, waiting for the next trial, a violent thermal shock. The steel rod, forged under immense pressure, now enters a furnace for a trial by fire. This is a thermal execution designed to rewrite its atomic DNA. The temperature climbs to 900 degrees Celsius. Inside the glowing metal, the rigid iron lattice relaxes, allowing carbon atoms to break free and spread evenly throughout the structure. This is the austenite phase, a state of perfect chemical uniformity. But this order is fragile. The secret to strength lies not in the heat, but in the shock that follows. A violent transition. The steel rod exits the furnace and plunges into a bath of molten salt. The temperature drop is instantaneous. The evenly spaced carbon atoms are instantly trapped, forming a new, incredibly fine-grained structure called perlite. This molecular architecture gives the steel an extraordinary combination of properties. Immense tensile strength, yet the flexibility to bend without breaking. Hardness is tamed by elasticity. The atoms are now locked in a state of ideal tension, but without the final brutal act of physical shaping, this molecular potential is dead. The wire is still useless. With its internal atomic structure perfected, the steel is sent for a new ordeal, a physical execution. The process is cold drawing, and it is an act of mechanical cruelty designed to forge ultimate strength. The steel wire is pulled, not pushed, through a series of dies made of tungsten carbide, one of the hardest materials known. The wire enters the first die. It is crushed through the microscopic opening. The sound is a deafening screech, instantly smothered by a thick, solid lubricant that coats the metal. This happens at room temperature. There is no heat to help. This is pure, brutal force. The phenomenon is called strain hardening. As the steel is deformed, its internal crystal structure is compressed and elongated, locking the atoms into a new, denser, and far stronger configuration. Its diameter shrinks, but its tensile strength explodes. The wire then flies into the next die, even smaller, and the process repeats, a succession of ordeals. But this violence is controlled with impossible precision. A laser scans the profile of the wire as it exits the die. The system hunts for any imperfection. The tolerance for error is 0.001 millimeters, a deviation dozens of times thinner than a human hair. Any inconsistency triggers an instantaneous adjustment in tension. The machine ensures absolute uniformity under pressures that would tear lesser materials apart. The result is a steel nerve thin to its absolute limit, yet capable of bearing incredible loads. It is a filament forged by calculated violence, but this new strength has created a fatal weakness. A single drop of salt water is now enough to kill it. A steel wire, perfected to thousandths of a millimeter, now faces an enemy that cannot be measured by lasers: chemistry. To survive, it must dive into a bath of molten zinc heated to 450 degrees Celsius. The engineering challenge is absolute. How do you guarantee the immortality of steel when a single microscopic scratch in ocean fog means inevitable corrosion? The solution is not to create an impenetrable shield, but a chemical martyr. This is not a simple coating. It is a metallurgical transformation. The liquid zinc fuses with the steel's surface, creating a new hybrid layer that functions as a sacrificial anode. It is designed to die. In the endless electrochemical war against oxidation, the zinc will always corrode first, sacrificing its own atoms to preserve the steel core, a calculated self-destruction. But this chemical armor must prove its loyalty. The wire faces one final brutal inspection: the torsion test. A machine grips the filament and twists it violently on its own axis again and again, ensuring the coating refuses to crack or flake under stress. It must be one with the steel. The twisting stops. Encased in its new armor, the wire waits. Thousands of chemically protected wires are just raw material. Now, they must become a single organism inside a planetary stranding machine. This is a titan of mechanical synchronization, a spinning cage holding up to 100 massive spools, each weighing several tons. The process begins with the cable's spine. A central core is fed forward. Depending on the design, this is either another steel strand for raw strength or a polypropylene fiber for flexibility. Around this core, the machine begins its hypnotic rhythmic rotation. Wires are pulled from the spools under constant computer-calibrated tension, weaving them into a predefined helical pattern. This is not aesthetics. It is a principle of physics executed in steel. When the final cable is stretched under extreme load, the helical design forces the wires to constrict, pressing tighter against each other. Internal friction skyrockets. The entire assembly locks itself into a single, stronger unit. The structure is built in 3 concentric layers: an inner one to stabilize the core, a middle one to bear the primary load, and an outer shield designed for pure abrasion resistance. The synchronization is absolute. A single flaw, a momentary lapse in tension, would create a fatal weakness. The machine relentlessly effortlessly pulls the individual strands into a solid steel monolith. There is no room for error. Even a perfectly woven steel spiral hides microscopic voids. They are empty spaces, and they are the perfect entry point for an invisible killer: condensation. Moisture trapped inside a cable can cause silent, catastrophic corrosion, destroying the giant from within. So how do you protect the heart of the cable, a place where no tool can ever reach? The answer is not a coating, it is an injection. High-pressure systems force a thick synthetic lubricant into the cable's core during the final stranding process. This is no ordinary grease. It is a thixotropic compound, a material with a unique intelligence. Under normal conditions, it is a dense, viscous gel, but under the immense pressure of the stranding machine or the subtle oscillations of a bridge, it liquefies. It flows. This liquid state allows it to penetrate every microscopic gap, expelling all air and moisture before solidifying back into an impenetrable barrier. The lubricant also serves a second critical function. It dramatically reduces the internal friction between thousands of steel filaments as they shift and move. The cable can now breathe without tearing itself apart. The steel is now encased in a hermetic armor, a perfect defense. This single solid cylinder is finally ready for decades of environmental punishment. The cable is sealed and twisted, a perfect steel helix. But before it can be trusted with thousands of lives, one sample from the batch is sent to its execution. Inside a reinforced, soundproof chamber, the process begins. The cable segment is locked into the jaws of a colossal hydraulic machine. A low hum fills the room as the system activates. The tension climbs, slowly, methodically. The steel begins to sing a high-pitched, metallic note as its fibers stretch to their absolute limit. The hum of the hydraulics deepens into a groan. This is the point of no return, a violent snap. The sound is deafening, a shockwave of energy as hundreds of wires break at once. The test is over, the cable is destroyed, and the data defines its breaking point, ensuring the entire batch meets strict international safety regulations. Every meter of this steel has a complete history, traced from the specific iron ore mine to the exact temperature of its galvanizing bath. This level of certainty has a price. A single high-performance cable can cost between 50,000 and 200,000 euros, the price of a supercar for one steel artery. Once approved, these colossal spools are loaded for a global journey, moved by cranes powerful enough to lift locomotives. Thousands of tons of this steel now cross oceans, ready to become the invisible skeletons holding our cities together. They are already in motion. Giant spools crossing oceans, destined to become the invisible arteries of our infrastructure. This entire journey started from shapeless ore, transformed into the steel sinews of civilization, a process driven by the clash of two extremes. First, the brute force of an electric arc furnace reaching 1,600 degrees Celsius, a violent birth in liquid fire. Then, the cold mathematical elegance of planetary machines, weaving steel strands with millimeter precision. To visualize this hidden world, from microscopic stress to thermal dynamics, we fused documentary footage with advanced AI simulations, making the unseen seen. These expeditions into the heart of engineering are powered by curiosity. Your engagement allows us to continue decoding the marvels of technology. This journey from chaos to order leaves one final question. What was more powerful, the elemental fire that melts worlds, or the cold mathematics that binds them?